This is the second part of our lecture on voice transmission and a subscriber loop. Here in this part, we will discuss the voice channel, which is a part of a multiplexed channel, basically multiplex signal. So start with we just want to understand what is a voice channel. Basically the capacity of human ear is from 0 to 20 kilohertz, and there's a wide band of frequencies that a human can generate. Although we have a little bit difference in the ranges of uh, females and males, because the males have lower have a somewhat lower band, while the females have the higher band. But if we do not use 0 to 20 kilohertz of bandwidth to transmit, it is quite okay. And even using 4000 hertz or 4 kilohertz channel for voice, it is perfectly okay to use it, because with this much information embedded into the channel, it is quite easy to understand the speech, as well as it is quite easy to identify the speaker. Moving beyond that, if even we have a range from 200 to 3200 hertz, we get an optimum trade-off between the economics and the quality of voice transmission. Because while using this much band, uh, we can accommodate a lot of voice channels within a multiplex setup, frequency multiplex setup, while the quality of our voice is not affected that much. Now let's see what are the basic impairments of the voice channel. As we have already seen in our earlier discussion, the first part of this topic, that the major impairments in the voice channel are attenuation distortion, phase distortion, noise, echo, and singing. And we have already defined the meaning of defined distortion, and we know that distortion means that the received signal is not the exact replica of the sent signal. That may be due to the frequency response, or the variable delay of the channel, or it might be due to some noise, or it might be due to the non-linear performance of the electronics on the transmitter side or on the receiver side, which causes echo and singing. Attenuation distortion, we have already seen that it is the result of imperfect amplitude frequency response of the voice channel. It means that some of the frequencies are attenuated more than the other frequencies. Normally, the extreme frequencies, or it means that within the band, the lower frequencies and the higher frequencies are attenuated more than more, and higher frequencies are attenuated normally more. But when we send it on a carrier system, the which provides band limits, then the frequencies closer to the band limits are attenuated more than those frequencies in the middle. Now, how do we measure the frequency response of a voice channel? We have already seen that we have got two different ways of doing that, and there are two different standards for that. The North American standard recommends 1000 hertz to be used as the test signal, while the European standard recommends 800 hertz as the reference standard. But what happens that since we have different frequency. We have the frequency response of our channel is such that it has different effects on different frequencies. Uh, Now let's see why is it different. Number one, the performance of the channel itself. It might add some of the frequencies to be attenuated more than the others. The transducers on both the ends, the first transducer that converts our acoustic signal to the electric signal, which is the mic in a telephone set, and on the other hand, the other transducer which converts the electric signal into an acoustic signal, which is an earpiece or the speaker. They might have their own responses in addition to the electronics that is involved in between, which does include some of the multiplexers and the demultiplexers. In addition to these electronics, we have the performance of our mouth and ear also, which introduce some more differentiation of the frequency response to different frequencies. To simulate this different response, we use weighted networks. If we do not, and what is a weighted network? In a weighted network, what we do is that we we give a certain amount of attenuation to some frequencies and a less amount of attenuation to other frequencies intentionally, and engineer that and design it. So such systems are called the weighted systems. If we do not introduce a weighted system into our network, then it would be a flat network. There are two types of weighted networks basically. The C message network, which is used in North America, and sophometric weighted networks, which were introduced in Europe. And normally in Pakistan, the European system is used. And I've already said that the C message or the North American system uses 1000 hertz um, as the test signal, and sophometric system requires 800 hertz as the test reference. Here in this figure 5.7, you can see two curves. One is a solid line curve, which gives you some response of a C message, and the other one is a sophometric response, which is given as a broken line. What are these curves? Basically, these two curves are noise and annoyance curves. It means that as we increase the relative level in dBs of the signal, and we move from a frequency of 100 hertz and we go up to 5000 hertz, it is recorded at which frequencies people are experiencing annoyance. For example, uh, you can see approximately at minus 25 dBs for a C message testing. C message means 1000 hertz of signal is being used for testing. If minus 25 dBs of 1000 hertz signal is sent, sorry, if minus 25 dBs of 200 hertz signal is sent, then we would experience annoyance due to this much noise. As we go on increasing it, we come to a maximum at approximately 800 to 1000. The 800 hertz is considered as the test sequence at which we have a relative level of 0 dBs in the phosometric uh, system, which is adopted in Europe, while in comparison to that, at 1000 hertz, we have the American system, which considers 1000 hertz as the zero test level, or the zero relative level in dBs. As we further increase the frequencies, the uh, the annoyance level would vary, and it would vary just after 3000. It would a very low level of a relative level of power in dBs of such a signal would create annoyance, while at 1000 Hz even a 0 dB's relative level would be okay. Would create annoyance, but beyond that, uh, uh, if we go beyond that, or if we increase the level, it would definitely increase the annoyance level. But this is the minimum level at this frequency at which annoyance comes in. Now what we do is that we introduce weighting, and this is an example in figure 5.8. You can see the weighting in which we try to make this response as um, flat as possible, and the hashed region in between the two curves, the straight line and the C message response curve, uh, this gives us the noise advantage. In case of C message, we get a noise advantage of 2 dBs, while in case of sophometric systems, we get a noise advantage of 2.5 dBs. If we use data transmission instead of voice, the noise advantage goes away. Then it is of no use. Now let's see how can we find the weighting factor. If we have a bandwidth of 4 kilohertz, which is primarily used for voice, um, the weighting factor is given by 2.5 plus 10 log of B over 3.1, and this is given in dBs. And the answer to this is basically 3.6 dBs. And why did we use 3.1? Because we are using 3.1 kilohertz uh, of reference bandwidth, and 2.5 is the noise advantage in the sophometric system. That's why our weighting factor comes out to be 3.6 dBs. Now let's see what is the unit of noise measurement in a C message weighting system. It is called dBRNC. The dBRN stands for the decibels reference noise, while the dBRNC is referenced to 0 TLP, which is the dBRNC 0. The other way of measuring the noise, which is the European standard, it is called PWP, and PWP stands for picowatt sophometrically weighted. For sophometric weighting, the most common use of noise measurement is PWP, which is a linear unit, and it is referenced to 10⁻⁻12 watts, or 1 picowatt. We can also use dB units, that is dBmp or dBmps, dBm sophometrically weighted. We need to have a space in between this dBmp dBm, and we need to have a space here. Here we need to have a space. dBm sophometrically weighted. Now let's see what are the relationships for the conversion from one unit to the other. If we have minus 90 dBms, it can be converted to 2 dBrnc, and thus minus 92 dBm would be equal to 0 dBrnc. And minus 92.5 dBmp, now we are talking about the sophometric weighting, it would be equal to again minus 90 dBm. You can see that we are referring to the same absolute power value here and here. Here in this case, we are using the C message system, and uh, here we are using the sophometric weighting, which is for flat white noise, and one PWP is equal to minus 90 dBmp. The value in dBm would be equal to 10 log to the log of the value in PWP into 10 to the power minus 9 plus 2.5, and this 2.5 is the noise advantage that we get. Simply, on the other hand, for the C message part, we have got dBrnc, which can be calculated as 10 log of PWP into 10 to the power minus 9 minus 0.5 dBs plus 90 dBs. This is the conversion from a PWP to dBrnc. So the value in pico, if we multiply the value in picowatts by 0.56, we get the value in PWP. And to get the value in PWP divided by value in picowatts, we need to divide PWP by 0.56. Now, one more thing that we need to understand is that the general rule for passband in our signals is between 3 dB points. 3 dBs means if when the signal is cut in half, it is reduced to half. From the point it increases to the half of the maximum value, and to the point where it reduces to half the value, that is taken as the pass band, or and the bandwidth is calculated in this way. The voice channel is an exception to this rule. In the voice channel, we use 10 dB points, or where the power drops by 1/10. That is used. This definition is valid in the subscribers plant to the mainframe of the serving exchange.